Alright, hello everyone. In this video, I want to talk about something I think most people get wrong uh, about the butterfly effect. So, in the last year, I have researched about ordinary differential equation, or we can call it ODE. Um, in my research, specifically, I use neural ODE that I use on in LLMs, and because of that, I have studied about it, and I found something that uh, I think really interesting. Uh, like most of us have heard that this place maybe like a small change, butterfly flappings, its wings, like and in somewhere far away there is a storm. There is what we call the butterfly effect, but I think uh, uh, it's just the story version, and the real thing behind it I think is more precise and honestly a bit scary too. So in this video I think I want to go a bit deeper than that. So okay, let's start from the story a bit. I think so. In 1963, there is a meteorologist that his name is Edward Lawrence, and he wrote a paper called "Deterministic Non-Periodic Flow." The title itself is already the whole point of this talk, I think. So deterministic means purely determined, no randomness at all, and non-periodic means it never repeats. So the question is, like, how can something be 100% determined, but at the same time, we still cannot predict it? So it's like. But when so that is the question that I want to explain in this video. Why like deterministic doesn't mean uh, predictable. Then we have this. So this is the actual system that Lawrence used. The Lawrence equations. It's just three equations like here. Um, it connected to each other. That's why we call it a couple. Maybe I think let me read it slowly. So we can say in here like the change of x over time equals sigma times y minus x, and then the change of y over time equals x times rho minus z minus y, and then the change of z over time equals x times y minus beta times z. Uh, I don't. Maybe this looks like intimidating or something like that, but we don't need to memorize it. Like the important part is that these are non-linear equations. So because we can look like here we have x times y, um, and this multiplication of two variables, that's what makes it non-linear, and non-linear is where the chaos comes from, I think. So if it's just linear, it will be very, I think, boring and predictable. So like here, uh, then let's say we have this. These three numbers, uh, let's fix let's fix it. So Lawrence picked these specific numbers because with this number, the system becomes chaotic. If we change them, and sometimes it's not chaotic anymore. It's actually quite sensitive to which numbers we pick. And like this figure, it is what it looks like when it's simulated. On the left, x y z over time, very messy. And on the right, if I plot x, y, z together in 3D, it makes this shape, where we call it the Lorentz attractor. Um, People call it the butterfly because it looks like two rings. And this is actually also where the name butterfly effect comes from. Literally the shape, not just the metaphor. Then let's Okay, now here's the important part. So, how do we actually measure how chaotic something is? This number called Lyapunov exponent. So, written as lambda. So, the size of error at time t is about the size of the error at time 0 times e to the power of lambda t. So, delta x is just the difference, the error between two trajectories that started almost the same. And this formula says that error grows exponentially, so multiplied by e to the power of lambda t. So let's make this concrete with small work example. So how fast does tiny error actually blows up? Uh, with this example, so lambda given this. So given for the learning system, maybe we start with a tiny error. Um, Maybe then start with this, and then after the one we have then after t equals to 10, it can be and after t 20 we have the last value is, which is um already visible size error, I think. So we can look at this. So at t equals to 1, the error barely move, I think. And then at t equals to 10, it's still tiny, like less than million. But by t equals 20, the same starting error has grown to about 7 times 10 to minus 3. That is already a real visible size error. So this is the exponential blow up that I think this is the core of the whole talk. And then so 1 over lambda about 1.1, we call this tau the characteristic time. So roughly every 1.1 time units, the error multiplies by e about 2.7 times. Now, let's test this with a real experiment. So, but this time on a parameter, not the initial conditions. Remember, sigma was 10 before, right? So let's change it by an amount smaller than what a computer can even store reliably. So, so we have this sigma 1 equals 10.0, and then sigma 2 equals 10, then 14 zeros, then a 1. Then let me wait. 14 0. Then we minus, we have, which is smaller than double precision can reliably represent. So this is the basic difference. So this difference is basically nothing, right? So like 1 part in a quadrillion. So we can look at this figure. So for a while, blue and orange are literally on top of each other. So you can see, you cannot see two lines. So that's until about t equals 20. Maybe 40. Then suddenly, suddenly they separate each other. So at t0, it's quite identical. T20 basically still the same, right? Still same. Then T40 about maybe 45. It's completely different and unrelated. So a change smaller than what your computer can even store precisely becomes completely different outcome in less than 50 time steps. I think this is the real butterfly effect, right? So not the metaphor version. Then let's continue. Okay, so the natural questions, like, can we just use more decimal digits to fix this? Maybe let's calculate it. So we have this, the precision unit as a function of t plus your starting precision times e to the power of negative lambda t. And let's make this concrete, I think. So how many digits do we actually need to trust our predictions up to a certain time t? So we have lambda which is so machine precision. About it's like a normal computer, so double precision. If we try t close to 30, then it's required you need about 28 decimal digits just for the 30. Then if we try 60, it need about 40 decimal digits just for the equals 60. Okay, we can look at this. Normal computer only gives you about 16 digits, right? So to trust the prediction about up to t equals 30, we already need 28 digits. So by t equals 60, we need 40. It is insane if you think about it. So nearly impossible with standard hardware. Then so we actually tested these three charts using different precision levels. Epsilon equals 10 to minus 10, uh, minus 24, then minus 32. It eventually, with more precision, like the chart stays clean for longer, but even at 10 to minus 32, it eventually breaks into that colorful mess. So there's actually many trajectories spreading out. So, and then there is another way to say the same thing in bits instead of decimal digits. So the number of bits you need equals 53 plus 1.31 times t. So where a normal GPU only supports 64-bit arithmetic. So if we have 131, it's not even close. It's not double. Then okay, so the next part I think is actually the most interesting, but by philosophically. So if our computer can never be perfectly precise, so does that mean our simulation is not correct or valid? Actually, no. theorem that called the shadowing lemma. So the difference between the real path xn and our computed path x tilde n and is less than k times epsilon. So it is the real one, the real or exact trajectory. Then or computed or imperfect trajectory. Then k, it's just some constant number. So our computed path is an exact path, just for slightly different starting points nearby. So I think the next way to think about this, our wrong prediction is not really wrong. It's not a random noise too. It's completely valid alternative future, just from a slightly different starting condition. Like nature could have started there too. So like this figure. This is 100 slightly different starting points run together. At the beginning, they all look like one line around t equals 20. Then they explode into all these colors. Every single colored line here is mathematically correct and valid trajectory. Yeah, so given all of this, is there anything we can actually predict? So, uh, I think yes, but we need to change what we mean by predict. So, we have trajectory level, which is impossible beyond Lyapunov time, and then statistical level, still stable and still predictable, and then time average, which is ensemble average, that is called ergodicity. So trajectory level means that exactly like where will the point be at time t equals 100, which is impossible. And before this slide, I already showed that. And statistical level means that the average behavior, the overall shape, the distribution, it it stays stable, and this is called ergodicity. If I track one path for a long time and average it, I get the same answer as if I take many paths or at one moment and average across all of them. So that is the uh, the prediction statistically versus trajectory. Then here's the method that I think is quite clever, called SINDI, which is sparse identification of non-linear dynamics. It works well on chaotic data because it completely avoids the problem we've been talking about. So we have this. We can call. We can read it as the change of x over time is about x a bit after t minus x a bit before t divided by 2 times that small step. So we can uh, we can work with this example. Just 3 points close together. Suppose that we have and we measure So this is just a local slope using two nearby points. Uh, no, no long time simulation did it at all. And then we have this. The change of x over time equals theta of x times xi. If we calculate this, um, no, I think it's just something like this. Uh, it is a list of candidate terms. Which is something like this: x, y, x, y, x power 2, and then this is coefficients to find, something like this: 0, 0. The algorithm picks only the few terms that matter. So sparse means most coefficient is end up to 0. Uh, so that is just a big list of candidate functions: x, x squared, xy, whatever. So xi is the coefficients, and the algorithm finds which few of them actually matter. So that is the sparse part of the name. So, and because Cindy only uses local slopes, it never it doesn't suffer from the exponential blow up we saw earlier. And that is why it recovers the equations about the 0.03% error, even though long-term forecasting itself is impossible. So this brings us to relevant or these questions, especially with AI models claiming that they can forecast weather or markets or whatever. So based on everything we show, if someone claims they can predict a chaotic system for a long time, I think there is four things that they need to prove. Um, this so specify the precision. How many digits are you actually using? So then statistical, uh, not exact. So predicting the average or one exact path. Then it should also test beyond length of time. Uh, so uh, it's like did you test far enough, something like that. Then acknowledge the limit. So the honesty about what's impossible. If they cannot answer this, I think we should a bit skeptical about the claim. And then it's also uh, to be fair, this analysis has limits too. So we only tested one system and one parameter, and exponential error growth is not universal. So some system can grow as a power law instead. So it doesn't generalize to every chaotic system automatically. So to close this up, uh, so the system is fully deterministic, no randomness, but unpredictable in detail and at the same time statistically regular. And the overall pattern stable. which is weird combination, like so. But that is exactly what chaos is. So I think the real lesson here is knowing the law and knowing the outcome. These are two completely different things, even if you know the equations perfectly. So the future can still be in a very real or mathematical sense, unknowable, something like that. So okay, I think that's all that I want to talk this with you. So thank you.